Okay, so today's lesson is 2.7, and we're using the fundamental theorem of algebra. So the fundamental theorem of algebra basically says that every polynomial function of positive degree n has at least one complex zero. An nth degree polynomial equation will have exactly n roots or solutions or zeros, and that would include any repeated roots or identical roots. Complex zeros occur in complex conjugate pairs. So remember, when you have an imaginary answer, you can't just have one imaginary solution. You would have to have both of the complex conjugate pairs, so a positive and a negative. So let's talk about this second bullet point here where it says an nth degree polynomial equation has exactly n roots, solutions, or zeros. So if I have an nth degree polynomial, that could be, let's say we have a polynomial of 7th degree, for example. That would mean that it's going to have exactly 7 solutions. Now, in that set of 7, you could have some real numbers, you could have some imaginary numbers, and you can have the repeated roots as well. So I'll talk about those in a minute. But just remember that if you do have any imaginary numbers in your set of solutions, that they have to come in a pair. So you could have 2 imaginary, for example, and 5 real number solutions. Or you could have 4 imaginary and 3 real solutions. Or you could have 6 imaginary and 1 real solution. Or, of course, you could have all 7 be real, but any of those imaginaries would have to come in that pair. If the graph is tangent to the x-axis, this is where a repeated root occurs. So, for example, if you think back to learning about tangents in geometry, something that is tangent, it touches and then comes back, right? So you think of like a line being tangent to a circle or something like that. In this case, this graph of the parabola is tangent to my x-axis because it's just coming down and touching it in that one spot. So in this situation, let's just pretend that this value is positive 4. So if I had a set of solutions here, and let's say this was an x squared polynomial, meaning I would have 2 solutions. In this particular case, both of my solutions would be 4 because this is a repeated root because the graph will just touch the x-axis in that one location, meaning it's tangent. So that number there, this 0 here, is counted twice. So stating the number of solutions, when we want to find out how many solutions there are to a specific polynomial, we want to first make sure that our polynomial is in standard form. So that would mean that the first term is the highest degree, and then after that, each consecutive term is decreasing in order all the way down till we get to our constant. So number 1 is already in standard form, so then all we need to do is look at that lead term. Our lead term is of the 3rd degree, or a cubic polynomial. So this would tell me that I'm going to have 3 solutions for this polynomial. Now, if we take a look at number 2, for example, again, we're starting out with x to the 4th, x cubed, x squared, just x. So our lead term is the degree of the polynomial. Since it is a 4th degree polynomial, that tells me I'm going to have 4 solutions. Okay, so for number 3, this is a simple quadratic polynomial. So this would tell me I will have 2 solutions. But like I showed you in that other example before with the tangent, those 2 solutions could be the same number twice if it's a repeated root. And number 4, this is a 5th degree polynomial, so this one would have 5 solutions. And remember, these numbers of solutions include those repeated roots if there are any, and also those imaginary pairs. So decide whether the given x value is a 0 of the function. So in order to do that, you would simply need to synthetically divide out the number that's given, and you should get a remainder of 0. That would tell you that, yes, indeed, that number is a 0. So we were writing down our coefficients. We have a positive 1 for the x cubed, a negative 1 for the x squared, a positive 4 for our x, and a negative 4 for our constant. Then as we work through our synthetic substitution or division, which is the same process, we would drop down our 1, multiply it to this x value that we're checking, put it in the next column, add those up, multiply it by the 1 again, add the next column up, multiply that 4 by 1, and add it up. Now, because we did get this 0 here, our answer would be yes, x equals 1 is a 0 or a solution of the function. So we can try that again for another problem here. So we have a 1, 3, negative 5, and 8. Dropping down the 1, multiplying it by this 4 here that we're checking, adding up the next column, 7 times 4 is 28, adding up that column, and 23 times 4 is 92, leaving us with a 100. Obviously, this does not equal 0, so this would not be a solution, or you could just say no. Okay, number 3, another example here. Now we want to be careful here because we notice that there is no x cubed in our problem here. So if you remember back to when we did synthetic division or substitution, you have to put in that 0 placeholder where that x cubed would be, because the coefficient is technically a 0 if it's not there. Now we're dropping down the 1 and multiplying it by 0, adding up that column. 0 times 0 is 0, adding up that column, and 0. Now again, this time we do not get a remainder of 0. I ended up with a 3 as my last digit here, so this is a no. X equals 0 is not a solution or a 0 of that polynomial. And finally, number 4, I have x cubed, coefficient of 1, coefficient of 5, coefficient of 1, coefficient of 5. I'm going to start with my 1. 1 times negative 5, add those up. And then I do get a 0 here as my last number or my remainder. So this would be yes, x equals negative 5 is a solution or a 0 of this polynomial. Okay, so the next thing that we want to go over here is how to identify factors of a polynomial function if you are given the zeros. So we know that when we have factors, we can just simply equal them to 0 and use that zero product property to solve for those x's or those zeros or solutions or whatever you'd like to call them. So we can simply go backwards by putting these into that factored form. So, for example, if you know that x minus k is a factor and you set that equal to 0 to solve it, then you would actually end up with x equals k. So that would be your 0. So this would be your factor, and this would be your 0. Now notice the sign in front of the k here, there's a subtraction sign. So when you actually solve, you would get just the positive. So what that looks like when you put it into factors, if this 0 is an 8, that means your factor was x minus 8. Because if you solved that factor using zero product property, you would just get x equals 8. The next 0 is negative 3, which means our factor would be x plus 3. Same idea. If you solved that factor using zero product property, you would have gotten that 0. And then finally, our third factor has to be x minus 4 because our 0 was positive 4. So for example, to check one of these, to explain why that works, let's say you had the x minus 8 equals 0, and you were going to solve it. You would get x equals 8, which is what we were given, right? So we're just going backwards. So if you remember when we factored and then we solved the factors to find our zeros, we're now given the zeros and we're going backwards and rewriting them as factors. Okay, number 2, this would be x plus 9, x minus 2, and then notice that we have a second 2 there. There would be another x minus 2. So the better way to write this would be as the square of a binomial, so you would write x minus 2 squared. And this would typically represent that there's going to be a tangent portion of that graph. So that graph would be tangent to the x-axis at the value of 2. Okay, so now the next one here, sometimes this one trips people up. We have an x plus 1, an x plus 2, and then for the 7, that's x minus 7. Now, a lot of people don't know what to do with the 0. Now, if you think about it, if you had x plus 0 or x minus 0, the plus or minus 0 would just kind of cancel itself out, and you would just be left with an x. So if you're doing a problem like this, anytime you have a 0 as your 0, that means your factor would simply just be a single x by itself. There's no plus or minus involved. And then finally, this last one here, we have x minus 10 and x plus 6, but you'll notice that there's this imaginary I here. Now remember, even though they're only giving us one I, which you might think is x minus I, they always occur in a pair, conjugate pair, so that means you also have another 0, even though it's not listed, it has to be there, of negative I, and then that factor would be x plus I. Okay, so moving along. So now we're going to use these factors to help us write a polynomial function of least degree that has real coefficients, the given zeros, and a leading coefficient of 1. So we're going to start out by just basically writing those factors. So we're going backwards from the, normally we would take our whole polynomial, we would figure out, how to divide a factor out, how to finish factoring it, then we would solve for those zeros. Well, we're going to go back up the ladder, so to speak. So we're going to have our zeros, we're going to write them as factors, and then we're going to multiply those factors back together to get that entire polynomial. So our first one here, number 1, x minus 2 would be the first factor. X minus 1 would be the second factor for that 0. And then the 0 of 4 is going to give us x minus 4. Now, once you multiply 3 binomials together, we did this in an earlier section, just simply multiplying here, you're going to pick whichever 2 you would like to start with, multiply those, get the product, and then multiply that answer to the third binomial that you haven't used yet. So it doesn't matter which 2 you start with. I will start with the first 2 here. Okay, so if I multiply these 2 together, I'm going to have x squared minus x minus 2x plus 2. And of course, when I combine my like terms, that's going to give me x squared minus 3x plus 2. And now I'm going to multiply that to that x minus 4 that's remaining there that I still have not multiplied yet. So now at this point, I'm going to now take my x squared and multiply it to each of these terms here. So I would have x cubed minus 4x squared. Then I'm going to take the negative 3x and multiply that to each of those terms. So negative 3x squared and plus 12x. And then finally the 2, so I would get 2x minus 8. So once I'm done with that, I'm just going to combine my like terms. Now, because of the way I set up my answer, they're already kind of stacked together, so it's very easy to combine my like terms now. So I know that I now have f of x equals x cubed minus 7x squared plus 14x minus 8, and that would be my polynomial. Okay, so if I go to number 2, I'm going to start out with my factors, x minus 1, x plus 4, and x minus 5. So again, I'm picking 2 to multiply together first. Doesn't matter which 2, I'm just choosing the first 2. I get x squared plus 4x minus x and minus 4, and I'm going to combine those 2 like terms here in the middle, and that's going to give me x squared plus 3x minus 4. And then I'm going to multiply that by my remaining binomial, the x minus 5. So x squared times x is x cubed minus 5x squared. Then I go with the 3x. So I have 3x squared minus 15x minus 4x and plus 20. Combining my like terms now, my final polynomial will be x cubed minus 2x squared minus 19x plus 20. All right, so we got a couple more of these, but they're going to be a little bit different on the next couple. Well, number 3 is not too bad, so I would encourage you just if you're kind of working alongside of this video, I would maybe pause it and just check to make sure we're getting this one right. So x plus 2, x plus 4, and x plus 7 are your 3 factors. I'm going to just go ahead and multiply my first 2 factors together. So that will give me x squared plus 4x plus 2x plus 8. Combining those 2 like terms in the middle gives me x squared plus 6x plus 8. And now I'm going to multiply it to my x plus 7. So I get x cubed plus 7x squared plus 6x squared plus 42x plus 8x plus 56. Combining all those like terms there, I have a cubic polynomial, x squared plus x cubed plus 13x squared plus 50x plus 56. Okay, so now if we take a look at number 4, it looks similar, right? We're going to write out our factors here for this one. The only catch is we have 2 imaginaries. Now this time they did give us both of the complex numbers in the pair. They gave us both parts, that complex conjugate pair, so we don't have to worry about presuming what the other one is. They're both there already. So we're going to start out with x minus 8, and then of course we would have x plus I and x minus I. Now in all the previous problems, since we were only dealing with real numbers, it didn't matter which 2 binomials you multiplied together first. But this time, because you do have that complex conjugate pair, you definitely 100% want to multiply together the complex conjugate pair. The reason for that is when you FOIL those together or you multiply them together, your i's will all cancel out, which is what you want to happen. So if you multiply the 2 x's, you get x squared, but then you're going to have minus ix plus ix, and then you're going to have minus I squared. Now, of course, those 2 ix's in the middle there are going to cancel. Then you're going to have x squared minus, and don't forget, I squared is really equal to -1. So this now becomes x squared plus 1. And now that's going to be much easier to multiply to that x minus 8. So when you multiply these 2 together, you're going to get x cubed plus x minus 8x squared minus 8. But of course, you need to put this answer in standard form. So we have to make sure that we reverse those 2 in the middle because it happened that the way I did it, they didn't line up the right way. So I'm going to put my cubic term first, followed by the minus 8x squared plus x minus 8. Okay, so a few more practice problems with these. I think there's 2 more left. Now here is another example. We have x minus 2 and x plus 2. That's kind of a no-brainer. But then they're giving us this one imaginary answer. So we know that there's a negative 6i. There must also be a positive 6i. So now I can write my 2 factors as x plus 6i and x minus 6i. So that's the catch there. You have to make sure you catch that and you make sure you have both. So now when you do this, you definitely want to multiply together those 2 conjugate pairs, and then you're also going to FOIL together the 2 real number binomials, and then you can multiply the two products together. So for these two, since you might notice that these are two binomials that are the same except they have opposite signs, so that's sort of like a difference of two squares pattern. So you remember that pattern, you can just skip to x squared minus 4 as your product there. And over here, similar situation, you're going to get x squared minus 6ix and plus 6ix are going to cancel, and then you're going to have minus 36 I squared, which of course is just going to change to positive 36 because that I squared is really a negative 1. So now we can multiply these two binomials together, getting x to the 4th plus 36x squared minus 4x squared minus 144. And of course, those middle two are like terms that can be combined. So I have a quartic polynomial, x to the 4th plus 32x squared minus the 144. Okay, and then finally, this last one here, we have three real numbers. So we don't have to worry about any imaginary conjugate pairs. The 3 is simply going to be the factor x minus 3. The negative 2 will be the factor x plus 2. And because we have the 0, we're just going to need that single x as well. So whatever way you want to multiply these is fine. If you want to choose like the first two and do that and then FOIL, or you want to FOIL and then distribute the x, it really is up to you. So if I do it this way, I have x squared minus 3x. And now I'm going to multiply that with my x plus 2. So x squared times x is x cubed plus 2x squared minus 3x squared minus 6x. Of course, the middle two will combine. So my final polynomial here is x cubed minus x squared minus 6x. Okay, so the next section, we're just going to make sure we know how to do those factors. We're just identifying the factors of the polynomial function here, making sure that we don't miss anything with zeros or imaginary numbers. So this first one, the simple three factors are x plus 3, x minus 2, x minus 8. This one here, we have just a single x for the 0, and x minus 9, and then we need that conjugate pair, so we're going to have x minus 2i and x plus 2i. All right, and then this third one here, we also know that we're going to have that other I value that goes with this negative I. So we have two real factors, x plus 5 and x minus 4, and then we have the two complex ones, x plus I and x minus I. Okay, so now these last four, we would set up those factors and then multiply them out. So x minus 4, x minus 7, x plus 1. And if I were to multiply this out, which I'm not going to do just to save some time here, because you have three x's, you know it's going to start with an x cubed. Number 2, your factors are x minus 9, and x plus 3. And once again, you have three x values, so you know that your lead term there is going to be x cubed when you multiply them out. Okay, number 3, you have x plus 2, x minus 4i, and of course you will also have the x plus 4i. And again, three x values, so this would also be a cubic polynomial when you multiply it out. And then this one here, we have x minus 8, x plus 6, x plus 3i, and then of course the conjugate pair, x minus 3i. This time we have four x values, so if we multiply it out, we would get a fourth degree polynomial. Okay, so now finding the actual zeros. Okay, so this is kind of, before we were given the zeros and we were working backwards to write down what the polynomial would look like. but now we are going to find the zeros. And we did do a little bit of this in the previous section. In the previous section, our instructions were to just find all the real zeros, but there was a couple problems that we kind of ran across where we were able to continue solving it, and we found that the last couple answers were imaginaries. So that's what we're going to do here. We're going to find all the zeros, regardless if they're real numbers, imaginary, repeated roots, whatever, irrational. Okay. So when we're finding zeros, if we're not given something to start out with, the two options are, one, to find our list of possible rational zeros. And if you remember, that list was basically your factors of your constant. So the factors of 20 are 1, 2, 4, 5, 10, and 20. But of course, you needed to make sure you included both positive and negative of all of those. And then if there were multiple factors of your lead coefficient, in this case, it's just 1, so we don't have to worry about it. But if it were a number other than 1, you'd have to list all those factors of 20 over the different factors of that number. Now, once you get this list, I have 6 numbers and they're all plus minus. So there's really 12 options there. I would then synthetically divide out randomly some of those options to see which one will give me a remainder of 0. And then I would know that that number is a 0. Okay, but because we have graphing calculator to use, rather than spending a lot of time guessing and checking, we can put this into our calculator. Now, we know we're going to have 3 solutions. So before I put it in the calculator, I like to just set myself up so I know how many I'm looking for, right? So when I go put this in the calculator, I'm going to put in x cubed plus 5x squared, minus 4x minus 20, and I'm going to graph it. And I'm looking for 3 x-intercepts. So I have 1 at the 2, the positive 2 here. I have 1 at the negative 2, and then 3, 4, 5, 1 at the negative 5. So all 3 of my x-intercepts were clearly visible on my graphing calculator. So at this point, I really don't have any more work to do. If I was only able to find 1 or 2 of these, then I might have to divide them out to solve for the remaining one. Okay, so let's take a look at number 2. So now number 2, again, I'm looking for 3 solutions here. And I'm going to start out with my factors of 25 because that list of possible rational zeros would be positive or negative 1, 5, and 25. So I know that any of my real number answers that are rational would have to be either positive or negative 1, positive or negative 5, positive or negative 25. And I'm looking for 3 solutions. Now, I may also have imaginary solutions here or irrational numbers, which wouldn't show up in my list. So we are still looking for 1, 2, 3 answers here. So we'll start out with the calculator. Now, I just realized on my last question that my window was adjusted. So a good way, I could go back to my window and just readjust it to the default settings, or you could reset your calculator. But I'm going to go negative 10, 10, and 1, negative 10, 10, and 1. And now I'm going to go to my graph, my y equals, and I'm going to type this one in. So I have x raised to the 3rd power minus x squared plus 25x minus 25, and I'm going to graph that, and I'm looking for 3 x-intercepts. Now, unfortunately, I only have 1. It looks like it's going through the positive 1, which would be on my list. I'm checking my chart here, my table. It is definitely a 0, so I have that 1 going for me. X equals positive 1. Unfortunately, the other 2 did not show up. It's possible it could be 25 and negative 25 since those wouldn't be showing up on my grid. You could go through your table and scroll up or down or change your window to see if they're there. But that kind of is actually a little time consuming to kind of click down. And most likely they're going to be imaginary or rational anyway. So if I just divide out my 1, I will be able to solve for those remaining 2 solutions regardless of whether they're imaginary or they're real. So I'll be able to find them whether they were on the graph or not. So I might as well just go ahead and do that. So I'm going to drop down this 1. 1 times 1 is 1. Adding those, I get a 0. 0 times 1 is 0. Add those, I get 25. 25 times 1 is 25. Add those, I get the 0 as the remainder, which confirms that 1 was one of my zeros or solutions. So now this remaining part here is x squared plus 0x plus 25. And if I set it equal and simply algebraically solve this, I will get my remaining 2 solutions. So I have x squared equals negative 25. I want to square root that now. Now every square root has 2 answers, a positive and a negative, and square root of 25 is 5i because of that negative. So my remaining 2 solutions are 5i and negative 5i. So it's a good thing I didn't waste time looking for them on the graph because I would have never found them. Okay, so let's go down to number 3. Okay, so once again, number 3, it's in standard form. My lead term here is an x to the 4th, which tells me I'm expecting to have 4 answers, 4 x values here. So that's what I'm looking for, my 4 zeros or solutions, which hopefully are also x-intercepts. Now, if I were going to use my calculator, then obviously I can do that. If I needed to find my list of possible rational zeros because I didn't have a graphing calculator, I'd be choosing from the numbers 1, 3, 9, and 27, both the positive or the negatives. So obviously we have technology here available to us, so we might as well use it. So we don't have to guess and check from those 8 numbers. So if I'm typing this one in, I have x raised to the 4th plus 4x raised to the 3rd minus 6x squared minus 36x minus 27, and I'm going to hit my graph. So we'll notice this problem. It is intersecting the x-axis in 2 locations at the positive 3 and the negative 1. So we have positive 3, negative 1, which were both numbers from my list here, so I know that they're accurate. And then, whoops, where's my graph? There we go. And then I notice at this spot here at the negative 3, the graph is tangent to that x-axis. So it's coming down and touching that x-axis and then going back in the other direction. So this negative 3 is still considered a 0. However, this is one of those repeated roots. So it's going to count twice. Okay, now sometimes people like forget about that and they just, maybe they got the first 3 here because they saw them, but they forgot that this third one's going to count double. So let's just say that happened, right? Well, if I want to divide out the 3, for example, that we had, I could divide out my 3. What's that, 60, 45. And that's 9. Okay, so we divide out the 3. Now I'm going to work off those numbers and divide out the negative 1. Okay, so that's divided out now. And then I'm going to divide out the negative 3 that I saw because we know that it was like touching at that spot. So I divide out my negative 3. And then I would say, okay, now I got to solve this last part to get my remaining answer. Well, this is my constant. This is my x. This is x plus 3. And then if I solve that, I would just get x equals negative 3. So if you forgot that that root is counted twice when it's tangent, then you could have just divided out all the ones that you did know, and then whatever is remaining, you can still solve for, even if it's a real solution or repeated or whatnot. Okay, two more of these, I believe. Okay, now we're going to get into some more imaginary solutions. So now this one, we know that we're expecting 4 solutions here. So I'm going to set up my spot to write my answers down. I'm expecting to have 4 x values here. And if I were using that list of possible rational zeros, I would just need my factors of 6, which are 1, 2, 3, and 6. So I know that any of those numbers, either the positive or the negative version, could be possible rational solutions here. But I'm going to use my calculator to narrow down the choices because I don't want to spend a lot of time guessing and checking and getting things that aren't working out. So if I type in x raised to 4 minus x raised to 3 minus 5x squared minus x minus 6, and graph that. Now we'll notice this time that in 2 locations, it does cross through at the -2 and the +3. However, we can't see any more x-intercepts, but you see how there's this other little like curve here? That tells me that the other 2 solutions are imaginary. So I'm going to simply divide out the -2 and the 3 and then solve the remaining equation to get those 2 imaginary solutions. So when you divide out that -2, obviously we want to put all our coefficients in here. And then we're going to start out by dropping down that 1, multiplying, adding them up, multiplying, adding them up, multiplying, adding them up, multiplying. We got the 0 for the first one, so that's good. Now we're going to divide out the 3. So multiplying, adding them up, multiplying, adding them up, multiplying, adding them up. That one confirms the 3. And so now we can use this remaining part here for x squared plus 0x plus 1, and we can solve that. So when I solve it, I get x squared equals -1. Of course, when I square root both of those, I end up with x equals positive or -1i, which is really just an I. So plus I and -I would be my conjugate pair for those remaining 2 solutions. Okay, and then we have one more. So again, x to the 4th, right? So that means we're going to have 4 solutions. Okay, my list of possible rational zeros would be positive or negative, and then the factors of 8. So 1, 2, 4, and 8. So those numbers we're looking out for when we do the graph. So we type our equation into the graph. So we go to y equals, clear out the one that's in there. Then we're going in x raised to 4 plus x raised to 3 plus 2x, oops, oh, I hate when that happens, oopsie, 3 plus 2x squared plus 4x and minus 8. Then we graph it. Hopefully we get a bunch of those x-intercepts to show up. Well, we have 2 that are showing up at the +1 and the -2. Both the +1 and the -2 are numbers from our rational zero list. If you weren't sure, you could always go to the second graph, which gives you your table, and you can see those y values of 0 there next to the -2 and the 1, confirming that those are indeed solutions or zeros. So now the other 2 are most likely going to be imaginary solutions. It looks like it's possible because there's a pair. So we're going to divide out the 2 numbers that we did get and we confirmed, and then we're going to solve for the remaining 2. So I'm going to divide out the 1 first. That's confirmed with that 0, and then I'm going to divide out the -2. That is also confirmed. This leaves me with the equation x squared plus 0x plus 4. And when I go to solve that, I get x squared equals -4. which when I do my square roots, I get positive and negative 2i. So positive 2i and negative 2i would be my remaining two solutions or zeros. Okay, so in the last page here is what happens. We've gone over how to solve for rational zeros, and we've also used those rational zeros to help us find those imaginary pairs. But sometimes you get solutions that are are real numbers, but they're irrational. So they're not whole numbers, they're not integers, they're not fractions. They're those like kind of long, crazy decimals, right? And it's very difficult to do work by hand to find those. So we're really going to use our calculator to approximate these zeros when they're irrational and difficult to find by another means. So we're going to use our graphing calculator here to find the real zeros. So we're not going to use the graph calculator to find imaginaries, okay? We already went over how to find those by dividing out those real ones. So right now we're only going to focus on the real zeros, but they're going to be irrational, so we're going to round the answers to the nearest hundredth, which is 2 places. So again, this is a cubic function, so I'm expecting to have 3 x values here, 3 solutions or zeros. So let's put it in the graphing calculator and see how many of those are something that we can actually find. So we go to our y equals, we're typing in x raised to the 3rd power minus x to the 2nd power minus 5x plus 3. Now when we graph it, we can see all 3 zeros or solutions are also indeed x-intercepts. They all cross through the graph visibly, so they're not imaginary. However, if I go to my table, I will notice that I do not have any zeros in my y column, which means none of these integers or whole numbers here are going to be the solutions or zeros. So if you think about this one for a second, like if you were to make that list, right, the possible rational zeros would have to be positive or negative 1 or positive or negative 3. And so even though it kind of looked like it might have been going through near one of those, it's not. It's not on positive or negative 1. It's not on positive or negative 3. So then we know that these are going to be some kind of an irrational number, which is going to be some kind of a non-terminating decimal. So how do we find those? Well, there is a button on the calculator that does say trace, and that gives you this little cursor, and you can kind of like use your arrows to move around the graph. And while it's moving along the graph, it'll give you the x and y coordinates of whatever point it happens to be on at that time. It's a decent tool to use. Like right here, you can clearly see that the y-intercept is 3. But the problem is, because of the calculator being pixelated, every time you hit the arrow, it's going to jump several points. And it's very difficult to get it to land exactly where you want it, which would be to have a y value of 0. So you'll notice, like if I scroll it down here, I have negative 0.4. If I go back a little that way, it jumps, you know what I mean? So unless you can get it to be y equals 0, the x value is kind of useless. It's just giving you random points on this graph. So to get the exact x-intercept, or known as a 0, you're going to use the second trace, which gives you this calculate menu. And notice the second option down the menu says 0. So we're going to find a 0, so we're going to use this option. So I'm just going to press the number 2. You could also arrow down and hit enter, get you to the same place. Now, you'll see down here at the bottom, it says left bound. And then we're going to enter a value there, and then it's going to say right bound. So what the calculator is asking you for, you're saying, okay, calculator, I want you to find a 0 of this graph, but there's 3 zeros here. There's 3 x-intercepts. So the calculator doesn't know which one you want to find. So you need to properly tell the calculator which one you want it to kind of hone in on. So if I wanted to find this one here on the left, it looks like it's near negative 2 somewhere. I need to pick some value to the left and some value to the right on the x-axis of the 0 that I'm trying to identify to tell the calculator this is the one I'm trying to find. So on the left, I'm going to pick -3. And my calculator is going to put this vertical kind of barrier there. And then I'm going to pick a number to the right. So I'm going to pick -1. And then you'll see another barrier. So you'll notice that now the calculator has kind of said, okay, these are the parameters. I'm going to look for a 0 between these two barriers that you've identified, or these two parameters. And now it's saying guess. And all you have to do is hit enter again. And now it's going to give you that 0 value. And you'll notice that the y is equal to 0. So that's how you know this is indeed a 0 or a solution of the graph. So -2.086, which would round to -2.09. So -2.09. So let's try it again for the next one. So if I was moving my cursor along, I'm just using the normal trace feature right now, but I can get to 0.6. If I hit my arrow one more time, I get to -0.1, but still not exactly on 0. So I'm going to use my second trace function here. So second trace, I'm going to get my calculate menu. I want to identify another 0 of this polynomial. So I'm going to press number 2. And now I'm going to give the calculator new parameters to work with. So I'm going to pick something on the left. So I'm going to pick -1. And then I'm going to pick a number on the right. And I don't like to pick anything too close. And I do notice that when I pick values that are only like 1 or less than 1 away, the calculator sometimes won't work properly. So I try to at least have them like at least more than 1 unit away. So this one, they're like 3 units away from each other. But anyway, so there's only one x-intercept between those two parameters that I've set up, those two vertical barriers, right? There's only one x-intercept or 0 between them. So now where it says guess, I'm just going to hit the enter saying, yeah, go ahead, guess. And it's 0.57. And we can see the y equals 0, so we know that that one is 0.57. So 0.57. Okay, and then the third one, I'm going to scroll over here with my trace. Okay, again, this one, it's really close, 0.57. If I hit it again, it goes to -0.75. Trace is kind of useless when you're looking for exact answers. So I'm going to go to second trace, number 2, my 0 again. I'm going to tell the calculator, I think it's between 2 and 4. 2, +2, +4. All right, now the calculator is saying, should I guess? And I'm going to say, yes, guess, enter. And there's my 0, +2.51. All right, so let's practice this again with another example. So if we take a look at number 2, okay, this time we'll notice that we do have an x to the 4th. So we're expecting to have 4 answers here. Now remember, it's possible that 2 of these or all 4 could be imaginary pairs, right? So let's see what the calculator shows us, and then we'll go from there. So going into my calculator, go to my y equals, clear out the previous polynomial equation, put in x raised to the 4th minus x raised to the 3rd minus 4x squared minus 3x minus 2. There's my graph. Now I can see it crossing through at 2 locations. I don't think that they are factors of 2. I do not see any zeros in my table, so that pretty much confirms it for me there, that these are going to be some kind of a decimal or irrational 0. So I'm going to use my second trace. I'm going to tell the calculator I'm finding yet again another 0, number 2. And now I'm going to give my calculator those parameters. So I'm going to pick -3. You could probably even pick -2 if you wanted to. And then I'm going to go for 0, which is the y-axis. So even though you can't see the line because I picked 0, you can see that little arrow up there showing that that's the line there. and then I'm just going to hit enter so that the calculator can do its work. Okay, so that 0 is negative 1.27. So the first one is negative 1.27. Back, I'm going to find this one over here that looks very close to that positive 3. So again, second trace. I'm finding another 0. I'm going to pick a number on the left, which would be positive 2, a number on the right, which would be positive 4, and then yes, enter. I'm going to have the calculator guess what that value is, and it is 2.855, which will round to 2.86. Okay, now the last two, because we can tell there's no other intercepts that we can visually see, so we know the last two solutions then would be an imaginary or complex pair. Okay, so then this next problem here, we would have 3 x values. Let's see how many. Now, notice this. If I were to list my possible rational zeros here, all I have as an option is a plus or minus 1. And since I need 3 solutions, it's very unlikely that these are going to be the solutions, right? So putting this into my calculator, I'm going with x cubed minus 2x squared plus x plus 1, graphing it. And I only have 1, and it's not on a whole number, that's for sure. It's not on 1 or negative 1. So I'm going to go right to my second trace to identify that one using the second option, which is 0. I'm going to pick negative 2 as my left bound, and then I'm going to pick 0 as my right bound, and then I'm going to hit enter to get that value, and it's negative 0.465, so negative 0.47. So negative 0.47. Now we know from looking at the graph that there's no other x-intercepts, and there is a curve there which tells me that there are 2 imaginary zeros or solutions, and they would have to occur in that complex conjugate pair. Okay, and then our last example, this one is an x to the 4th. So I'm looking for 4 different x values here. If I were to make that list, I would be looking at my possible rational zeros of positive or negative 1, 3, 9, and 27, since those are my factors of 27. So putting this last polynomial function into my graphing calculator, I have x raised to 4 minus x raised to 3 minus 20x squared plus 10x plus 27. Graphing that. I see it crossing through in 4 locations. Let me see if any of those are real numbers from my original list. So if I go to my table, I unfortunately do not see any zeros on here, so it looks like they're all going to be irrational. Luckily, we know they're not imaginary, right? So my first one here, negative 1, 2, 3, 4. It looks like negative 5, but the key is it can't be negative 5 because you remember this list here. If it's a whole number or an integer, it has to be 1, 3, 9, or 27. Negative 5 is not on this list. So that tells me it has to be an irrational number. So I have to do my second trace, unfortunately. So second trace, 0. I'm going to pick negative 6 for my left, negative 4 for my right, or no, negative 3. Maybe I'm going to clear that out, actually. Try it over again. I guess I miscounted. Okay, so my left bound, I'm going to pick, let's see, 1, 2, 3, 4, 5, negative 5. And then I'm going to pick negative 3 for the right. That looks a little better. Now I'm going to hit enter. Negative 4.09 is the first one. Negative 4.09. Okay, so now we're going to go to the next one. Second trace. Option 2, find the 0. And I'm going to pick my numbers as -2 and 0. So -2 is going to be my left parameter. 0 will be my right parameter. And then I'm going to guess it. -0.976, which would round to -0.98. -0.98. Back to my calculator again. This next one looks like it's between 1 and 2, so second trace. Option 2, find the 0. I'm going to say it's between 0 on the left and 3 on the right. And then I'm going to guess it. 1.469, so 1.47. And my final one, second trace. Option 2, find the 0. I'm going to say this one is 1, 2, 3, 4, 5. It's like very close to the 5. So I'm going to say 4 is my left bound. 6 is my right bound. And then I'm going to guess it. And now, sometimes people get stumped because you're like, uh-oh, the y doesn't say 0. It says -3.7 e -11. That is actually the number 0.000000000037. So it's a very, very, very small negative number, extremely close to 0 that it's written in scientific notation. So for our purposes, since we're only going to the hundredths place anyway, we can just kind of assume that that's a 0. And then we're just going to use 4.598, which would round to 4.6. Okay. So that is how you find your zeros on the graphing calculator.